We've done 5 principles about counting. We did the addition principle, the multiplication principle, the complement principle, the notice when two things are the same principle, and the count things multiple times in a controlled way principle. And then from there, we went through some of the ABCs that come up a lot in counting. Combinations, and permutations, and now we're doing the next step, which is to go through some more ABCs that come up in counting. And finishing up those ABCs, we'll move on to the inclusion-exclusion theorem, which I taught you back in set theory. And we're going to see how that connects back to counting problems. That is really a generalization of this complement principle. The inclusion-exclusion principle, if you remember how it works, is looking at the stuff that doesn't intersect, but they overlap. So it's kind of a generalized complement principle, and it's a lot trickier, but it lets you solve incredibly difficult-sounding problems. So we're going to get to that today. Once we're done with that, we're done with what I think are more or less the basics of counting. There's one more principle, which is really all on its own, and it's a really simple principle called the pigeonhole principle. And it basically means that if you've got 5 pigeonholes and 6 pigeons, that when you're all done putting your pigeons in the pigeonholes, there's going to be one hole that's got at least 2 pigeons. It's like a no-brainer principle. But there are surprisingly subtle things you can prove with that simple principle. And actually, there are such things as pigeonholes down in caves, these little niches out, and people used to raise pigeons in them. So if you ever saw a cave with pigeonholes in the wall, you'd see why they call this the pigeonhole principle. It looks just like you'd think. And when you're out of room for pigeons, right, yeah, right. There's a lot of flying pigeons around. Okay, the very last thing in this whole unit will be we're going to take all the stuff we've done on counting, the principles, the ABCs, the inclusion-exclusion, helper, generalization of the complement principle, and we're going to take it all and see how does this connect to certain kinds of probability questions. And probability is a course that you can take independent of a combinatorics course. And when it's typically taught, it's taught in a very, very widespread way, often getting into statistics, often getting into calculus and continuous kind of things. The probability that we talk about in this class is a subset of that course called discrete probability, a very small subset. And it deals with probability that you can actually count. And it's really almost a 10-minute lecture on probability at most, and really just let's do all the stuff we did before on counting, but relate it to probability. So it's not going to be anything new. It's just going to be applications of counting to probability in a discrete way. So the real principles are really today and next lecture, and then it'll be just probability as an application. All right, questions? All right, so here's our next one of our ABCs. We did permutations and combinations last time, and now we're going to do some variations on permutations and combinations, something you might call them generalized permutations or combinations. But here's one that I know you've seen before, and again, I'll do it by example. We'll call this a generalized permutation. And we'll talk about generalized combinations. What I mean by generalized is that permutations and combinations have a very specific meaning. You have a certain number of elements. Permutations are you take some subset out and you care about the order. Combination is you take some subset out and you don't care about the order. A generalized permutation allows some extra parameter here. You're allowed to take out an element more than once. In other words, it's not just a set of n elements. It might be a set of n types. Like you have 4 kinds of cookies. You're in a bakery. You want to take 6 cookies. How many different ways can you do that? So there you can repeat. You can take the same cookie many times. That's a different kind of problem. So if you add repetition as a parameter, you get a more generalized look at permutations and combinations. Okay? That's what we're going to talk about right now. So here's the first example. This example you've seen before. Let's say you've got 2 different things, zeros and ones. And you want to, in order, choose a bunch of these zeros and ones and put them in a list. Say a list of 5. 5 zeros and ones. So here's an example. Well, how many different ways are there to take zeros and ones and put them in a list of 5? It's how many binary numbers are there? You could list them all out. Start at 0, 0, 0, 0, 0, end at 1, 1, 1, 1, 1, 1. And you all know that inductively, this is kind of a straightforward idea, because if I tell you how many there are for 5, then if I add one more possible thing, a 0 or a 1. I can put a 0 in front of all the 5 cases and a 1 in front of all the 5 cases, and that gives me all the 6 possible cases. So it doubles every time. And we've done this in a lot of different contexts. We've seen that this is the same as the number of subsets, same as the number of binary numbers, length n. Let me write it down. Binary numbers, length n, equals number of subsets of a set with n elements. You can keep going and going. It's equal to so many different things. Let's say you have a big array in your computer, and if you know what I'm talking about, fine, and if you don't, it's okay. And you're going to cache into this array. You're going to store things into it in a very fast way. Well, what are the possible arrangements of this cache? Either the slots are filled or the slots are open. So it's like one big long binary number. So if you have a cache with n elements, the number of arrangements is also the same as this. I'll write that down. Arrangements of a cache with n slots. Whether the slot is filled or not filled is just whether there's a 1 in there or a 0's in there. And there's 2 to the n of these. We did that before. We did it in a different context before we even started talking about counting. So in some ways, this was the first kind of counting you'd ever done. You proved it by induction, you connected it to sets. All right, questions? Who remembers this? Everybody? This makes sense? Chris, you have a question?
Yep.
Okay. All right. An affirmative. Good. All right, here's my next point then. What does this have to do with permutations? This is the set of permutations of length n of 2 different items, where you can repeat the item. So if I just said you have 2 items, 0, 1, how many ways are there to permute those items? The answer would be 2, 0, 1, or 1, 0. But what about when I can repeat my selection? And I can go as long as I want. Then you get this generalized kind of formula. And actually, you can see the formula itself is not so bad. It's actually easier than other ones. Other kind of generalized formulas will be worse, but this one's easier. So let's think about this. We'll say this is also equal to the number of ways to permute 2 values. No, it's hard to write this. The number of ways to permute 2 values n times. I don't like that, but you got 2 different values. You can permute them n times, and I'll say in parentheses, repetition is allowed. Because obviously, you can't do something n times with only 2 values unless you're allowed repetition. Yeah, Tony.
You say number of ways for mute n value. I'm sorry, n values of 2 types.
That's better. The number of ways to permute. I like that. The number of ways to permute n values of 2 types with repetition. That's better. Okay, let me ask you a question now. If instead of binary numbers, I had 3 choices here, ternary numbers, 0, 1, and 2, instead of just 0 and 1, then how would this change? It would turn to 3 to the n. I have 3 choices each time. Every time I add a new column, I get 3 times as many as I got before. A 0 in front, or 1 in front, and a 2 in front. So that means every single time I add a column, it multiplies by 3, n columns, 3 to the n. So in general, if it's k types, then the generalized permutation with repetition of n values of k types with repetition is k to the n. Okay. So now that we have this, let's do a couple problems. Here's the 1-disk Tower of Hanoi graph. Remember this stuff? And then the next Towers of Hanoi graph, you take 3 copies of this and you connect them with edges. What are the nodes of a Towers of Hanoi graph? How do you represent them? Every value labeling one of these nodes is going to have a number 1, 2, or 3 representing what peg it's on, what post it's on. How many of those values are we going to have? Exactly equal to the number of disks in the problem. The 1 disk has 1 value. The 2 disk nodes would be labeled with 2 numbers, each of which is a 1, a 2, or a 3. That's exactly the same as the problem I just asked you a second ago. We have n values. We have 3 different possible types for each one. So there are 3 to the n nodes in a Towers of Hanoi graph. If there's 1 disk, there's 3 nodes. If there's 2 disks, there's 9 nodes. That means, remember the Towers of Hanoi, the fast solution is 2 to the n minus 1, right? What would be the ridiculously hard solution if you took off the edge from to 2 and from 2 to from? You'd go through everything, remember that? So it increases to 3 to the n. Right? So that's the worst it can get. If you don't draw the graph and you don't notice this, and somebody just shows you the Towers of Hanoi problem and says, hey, what's the worst this can ever be? You don't have a very fast answer. You might even know that 2 to the n minus 1 is something you can do, but you wouldn't know right off the bat that 3 to the n is the absolute, max. But if you make the graph and analyze it a little bit, now you can see that 3 to the n is the max. All right, questions about this? That's if you don't go backwards. I guess you can go backwards, and then infinity is the max. Just give it to a 5-year-old to play with, and you'd see that. Questions about this so far? All right, I want to do another problem. It'll get a little bit harder here. There's base 3 numbers of length 1. How many base 3 numbers are there of length n? 3 to the n, same as before. Now I want base 3 numbers of length n. I'm going to add a condition. With at least 1 0. Okay? Everyone understand? So that wouldn't count. That would count. Okay? I need at least 1 0 in this number. You can have 0, 1, or 2 in a base 3 number. Any numbers that don't have zeros don't count. Any numbers that do have zeros, I want to count. All right. Let's think about this. So this is a different problem, right? It's a harder problem. I'll give you a hint. The trick to this problem is to think of the complement. Whenever you have ORs in counting, ORs are harder than ANDs. It's always harder to do ORs than ANDs. At least 1 0. That means it could have 1 0, or 2 zeros, or 3 zeros, or 4 zeros. If you find yourself counting ORs, there might be a better way to do it. ORs are very hard to count because you have to divide them up into cases, and it really gets tricky. Sometimes it's the best way, but usually it's not. The best way to try to count is to convert something to ANDs, because if you can convert something to ANDs, then you can use the multiplication principle. If this has to be true and this has to be true, then you just multiply the 2 possibilities together. So let's try to convert this to a problem with ANDs in it. And that's the complement idea. The base 3 numbers that have at least 1 0 are the complement of the base 3 numbers that have no zeros. If they have no zeros, that's the same as the base 3 numbers that have 1s and 2s. Base 3 numbers that have 1s and 2s exclusively is the same thing as binary numbers. So let me write this down. At least 1 0, that's the same as all the base 3 numbers minus the ones that have no zeros. That's the same as base 3 numbers minus the ones that have all 1s and 2s exclusively. So we've converted our way of looking into a problem using complement that turns our ORs into ANDs. If you only use 1s and 2s, that means we want to know how many numbers are there of length n that have just 1s and 2s in them. That's the same as how many numbers of length n that have just 0s and 1s in them. So what's this number? This is 2 to the n, and this number is 3 to the n. And that's the answer. Base 3 numbers of length n with at least 1 0 is 3 to the n minus 2 to the n. Any questions about this? This kind of trick comes up a lot. It comes up on the problem set you're working on right now. I'll give you one example where it comes up a lot. It will save you a lot of time. If you're doing poker hands and you try to calculate the chance of a royal flush. Everybody know how to play poker? You all know how? Royal flush is 10 through ace of a particular suit. How many royal flushes are there?
4.
There's only 4. Okay? So the chance of getting a royal flush is 4 divided by all the possible hands you could get. 52 choose 5. That's an easy one. It's easy to calculate royal flushes. What if I said 4 of a kind? It's a little bit harder to calculate, but you could still count them up and do the appropriate choices and multiply appropriately. But if I tell you to calculate the number of ways to get exactly a pair, no better than a pair, just exactly a pair, that's tricky. Because once you choose the pair, you've got to be really careful that the other things you choose don't make you get something better. It's a little harder to count directly. But if you count using the complement principle, count what isn't a pair, you have an easier time. All right, so there's an example where it comes up. It comes up in a lot of examples. Always think about whether you can do the opposite more easily than the thing you're trying to do. Okay. Another example of this before we move on. How do we do this problem? On the theory that I'm connecting it to what we just did. I'm not starting something completely new and throwing you in the jungle. Think about what we just did. How are we going to figure out how many base 10 numbers there are with at least 2 zeros? What's our strategy here?
Total number of base 10 numbers.
Minus the things that don't have at least 2 zeros. Well, how do we say the things that don't have at least 2 zeros? The things with no zeros at all, and the things with 1 zero. So now we've got 2 things we have to subtract off. So at some point you start feeling here, well, is it worth doing the complement when the complement starts giving you lots of little pieces? Sometimes the complement gives you one simple thing to count. Sometimes the complement gives you a bunch of things to count. It's different in every case. See what happens here. Let's see how bad it's going to be.
They're ANDed together though, right?
ANDing is always nice, right? So the total number of base 10 numbers is 10 to the n. You got 0 through 9. Those are 10 different symbols, and you have length n. Okay, every kid knows that if you have 2-digit numbers, you have 100 of them. Right? 3-digit numbers, there's 1,000. We're going to subtract off all the numbers that don't have at least 2 zeros. That means the 10-digit numbers with no zeros and the 10-digit numbers with 1 zero. Okay so far? Now last time we did something very much like this. If there's no zeros, that means you just have the numbers 1 through 9. How many are there of those? 9 to the n, because you only have 9 possibilities, but they can go anywhere you want, and there's n slots. So that part isn't so bad. But this part's a little harder. Not too much harder, but a little harder. Now we want to figure out how many base 10 numbers there are that have exactly 1 zero. How do we count that? Is it 8 to the n? 8 to the n is almost right.
Well, you have to pick a place for your 0 first.
Yeah.
Of the, you're gonna have 1. So one of those n places is 0. Right.
But would it be 8 to the n then, or would it be here? Here's n spots. N spots. I have allowed 1 0 here. I'm going to stick it right here. If you're thinking, whoa, how do you know you're going to stick it right there? I don't. I could stick it any place, and we'll have to count that later. But let's say I choose this spot to stick the 0. Then how many ways are there for me to fill up the rest of the spots with 1s and 2s? Not 10 anymore, because I only have 9 symbols. 9 to the n minus 1. So once I pick my 0, I have 9 symbols to fill in the rest of the places. And how many places do I have left? n minus 1 other places. So once this 0 is chosen, I have 9 to the n minus 1 ways of making the number. But this 0 could be chosen in any one of n different spots. So it's n times 9 to the n minus 1. That's correct. 10 to the n minus 9 to the n plus n to the 9 to the n minus... You can read it better than I can say it. Let me stop for a second. Same problem, but it's got to have at least 3 zeros in it. Okay? Everybody with me? Same idea. So if you weren't following the last idea, now's the time to jump back in. We haven't left it yet. 3 zeros, at least 3 zeros. Same method. Take all the possible base 10 numbers. Subtract off the cases that have no zeros. Subtract off the cases that have 1 zero. And now, the mystery spot, we have to subtract off the cases that have exactly 2 zeros. Now this gets a little harder, but not much harder. All right, so let's look at it. Here's n slots again. Now we got to choose a place for 2 zeros. How many ways are there, if we have n slots, to choose 2 places? N choose 2. We don't care about the order that we choose them in. We're just going to try to pick 2 places here. So there are not n choose 1 this time, and I'm glad Seth mentioned that before, that n is really n choose 1. Now it's n choose 2. There's about n squared, more or less, ways for us to pick a pair of locations for the 2 zeros. And once we do that, how many ways are there for us to finish choosing the number? We got 9 symbols left. And now instead of n minus 1, it's n minus 2. So I'll write that down right here. N choose 2, 9 to the n minus 2. All right. I'm not going to do the next case because I'm hoping you can see a pattern here, even if you can't make the argument to yourself. So what's going to happen next? What's the next piece if I changed it to 4 zeros? What's the pattern? N choose 3, 9 to the n minus 3. And this is true, and it'll work all the way through. In fact, it'll work all the way through, and it'll give us this. It's screaming. It's screaming at me to write a formula down. Combinatorics is a great thing. Combinatorics is a great thing to suggest all sorts of unrelated connections. So here's one. What if I said, what are all the base 10 numbers that, well, here I had 3 zeros, right, that have at least 3 zeros. And what did I do? I subtracted off the cases that, right, that don't have 0 zeros, 1 zero, 2 zeros. I can add up all the base 10 numbers in the following categories. Base 10 numbers can be divided up into the ones that have no zeros. What's that? The ones that have no zeros? 9 to the n. No zeros. The ones that have 1 zero. And I'll write up here, no zeros. 1 zero. 2 zeros. How far do I go? No zeros, 1 zero, 2 zero, or n zeros, or they're all zeros. So I'll do the last 2 terms. Here's n minus 1 zeros, and here's n zeros. What do these last 2 terms look like? N choose n minus 1 times 9 to the n minus n minus 1, which is 1, times 9, plus n choose n times 9 to the, which is 1. See this formula?
So the first coefficient is n choose 0 for 9 or n.
Yes. Completely fine. Right. So it's completely symmetrical here. Let me write this as a summation. 10 to the n is the summation, I starting at 0, going all the way up to n, of n choose I times 9 to the n minus I. This represents each of these terms as I ranges from 0 to n. The first term is n choose 0, 9 to the n minus 0. The next term is n choose 1, 9 to the n minus 1. The next term is n choose 2, 9 to the n minus 2. This is a shorthand of writing it. All this says is that This sum is just a bunch of terms that all look the same. They're all n choose something times 9 to the n minus that something, and that something ranges from 0 to n. And this is true. We have a summation now that we never would have thought of straight up, but it came right out of this counting idea.
Can we generalize the 10 to the...
Absolutely. Turn this into an a, and this would be a minus 1. And Todd would remind me that we'd probably have to say that a has to be like greater than 2 or something, but something like that. And he'd be right.
As any fifth grader.
Chris is right. You can definitely generalize this. Now, where else could this have come from? What does it look like? It looks like the binomial theorem. Where does it come from, the binomial theorem? Watch. It's not so strange where it comes from. 9 plus 1 to the n. That's 10 to the n, right? Remember the binomial theorem? You get powers of n followed by the complement powers of 1. You don't see the powers of 1 here because they're all going to be 1. So you just see the powers of n going down. And what are the things in front of those powers of n? The binomial coefficients. Run the binomial theorem through on this. You'll get this. So I could have shown you this yesterday, but I didn't because I wanted you to see how to get to it through some other path. That's really what math is really all about. It's finding the same treasure through different paths and then understanding better how to protect it. In order to motivate this one, I'm going to do the most typical example that you'll see, that every math teacher throws on a problem set or a test sooner or later that uses this idea. And then I will tell you what this idea is. Because once you have the example, then the generalized idea will make more sense. But here's a typical kind of question someone will give you. Let's say you have a word like babaloo, or any word. Just make up a word. And the question is, how many different ways can I permute these letters? Can I rearrange them and get different words? Now, if all these letters were different, cab, how many different ways are there of arranging the word cab? 3 times 2 times 1, 3 factorial. It's n factorial. It's a problem that we did at the very beginning. It's one of the basic ABCs of counting. They're all different. You want to order them? There's 3 different ways to order the first one, 2 to order the second one, 1 to order the last one. 3 times 2 times 1. Simple, maybe. Here, the issue is...
I made it.
Here the issue is that if you just rearrange these in n factorial different ways, a lot of them look the same. Right? The 2 where we switch these 2 zeros look the same as these 2 zeros. Right? So you can't just say it's 1, 2, 3, 4, 5, 6, 7 factorial. Too many of those 7 factorials will be counted multiple times. So how do you do it? Well, there's 2 different ways to think about it based on the ABC tools that we've already learned, and they're going to be identical. So let's look at it in 2 different ways. Here's the first way. I've got how many different items here? 1, 2, 3, 4, 5, 6. I got 7 items. How many different types do I have? 1, 2, 3, 4 different types. 4 types. And more specifically, how many of each type do I have? I have 2, 2, 1, and 2. Okay? That represents the number of each type. You need a lot of information to solve this problem. You need to know how many different things you're permuting. You need to know how many different types. And you need to know how many of each type you have. So this is kind of in between allowing complete repetition and allowing just one copy. Now we allow particular numbers of copies of each. Everybody see how this is a more generalized version of the same kind of problem? Instead of any number of copies of the different types, we allow a specific quantity of that type. How do we count this? Does anybody have an idea? You have an idea?
7 factorial gives you 2 minutes, so you want to reduce it by
Okay, how much should we reduce it by?
the
7 factorial gives you too many. So this will be the counting multiple times in a controlled way style of doing this. 7 factorial gives you too many. Do you have an idea of how to cut it down?
No,
Tony?
I was just wanted to clarify. We're just finding the possible permutations. We're not actually trying to make this into words, right?
That makes
Right. It doesn't have to be a real word. Right. Lou Baba is going to be just fine. Every single permutation that has two A's in it is counted twice. So let's divide through by another 2. Every single permutation that has two O's in it is counted twice. 2 times 2 times 2. Every single permutation with an L in it is counted once. I'll divide through by 1. All you do to solve this problem is take the number of items, calculate the total number of permutations, and divide by the product of all the cases that get counted multiple times. In this case, 7 factorial divided by 2 times 2 times 1 times 2. Now,
If one of them occurred 3 times.
if one of them occurred 3 times,
Rather than
right. If this was 3, then you would have counted that one 6 different times for every single permutation. So what these really should be, to make it general, is 2 factorial, 2 factorial, 1 factorial. I'll do the same problem with some bigger numbers just to show you. Let's say I have 100 items, 4 types, 10, 20, 30, 40 of each type. How many different ways are there of permuting these items in unique ways? I got 10 of type 1, 20 of type 2, 30 of type 3, 40 of type 4. It's going to be 100 factorial divided by 10 factorial times 20 factorial times 30 factorial times 40 factorial. Right. Don't compute that number at home. All right, questions about this? This is one way of looking at it. This is the multiple counting way of looking at it. This is what Neil suggested, and we're going to look at it a different way in just a second. That will be equivalent, but a different way of looking at it. I've got 100 items. Okay, I want to permute them in any way I can, and I want to make sure that I'm only counting unique ways of permuting them. So one way to do it is to think of it as I got 100 slots. Okay? The first thing I'm going to do is put in all the different items of type 1. Put them in wherever you want. We'll call these A's, call these B's, call these C's, call these D's. So the A's can go in how many different places?
10 at a time.
There's 10 of them. They're going to go into any one of 100 places. 100 choose 10. I've got 100 choose 10 different ways of choosing different places in here for those 10 A's. Now, the order does not matter, right? That's the whole key, is that I'm doing combinations here, not permutations. I just switched a permutation problem into a combination problem by looking at it in a different way. That's a principle that's really important, and you'll see it come up again in a little bit. I am now thinking about permuting these items by doing the following thing. First, take all the items of type A and find a place for them in these 100 slots. I don't care what order they go in, because those are the ones that are counted duplicate if I care about the order. So forget about the order, just throw them in, but then it's a combination if you forget about the order. So it's 100 choose 10 to place the type A items. 100 choose 10 different ways. And when I'm done doing that, I'm still not ready to define my number. I still have 90 slots left. So let's move on and place the type B items. How many ways are there to place the type B items for each one of these 100 choose 10 ways that I place the type A items? 90 choose. Very good. And the next set? 70 choose 30. Everybody see what's going on? Let me make it clear if not everybody gets it yet. If I've chosen 10, then there's only 90 slots left. I pick 20 of those for type B. Now there's only 70 slots left. I pick 30 of those for type C. And now there's only 40 left. That should be pretty clear, right? Because once I put the A's and the B's and the C's in, I don't have any choice for my last item. And that makes a lot of sense that it should be just one. Now, if you're not really comfortable or used to these things yet, it wouldn't be obvious to you right away that this is the same as this, but it is. Just work this formula out and you'll find right away that these two are completely identical. This is not some weird paradox where we have to say which one is right. They're both right. There's nothing wrong with this argument. This is a fine way to do it, and that's a fine way to do it. And they're both reasonable ways. This is an example of turning a permutation to a combination and doing it step by step. Here's an example of the multiple counting idea. Different ways of thinking about the same puzzle, but they give the same answer. All right, let me convince you that it really is. 100 choose 10 is 100 times 99 times 98 down all the way to 91. Right? 100 all the way down to 91 divided by 10 factorial times, what's this? 90 down to 71 divided by, do you see what's happening? Do you see why it's the same as 100 factorial divided by 10 factorial, 20 factorial, 30 factorial, 40 factorial? The top here just concatenates these factorials all together in the perfect order. So what we do here is the same as what we do there. Questions about this? Another example of things being the same that don't seem to be the same at first glance. These are generalized permutations of k types with fixed amount of each type. Just so you see some notation, which you might see one day, if we call the different amounts of each type K1, K2, K3, and K4, then sometimes this is written like this. P of 100, comma, 10, 20, 30, 40. The 100 is the number of items, and the 4 different type values go afterwards. And I put semicolons there so you remember that these are the types and that this is the number of items. I don't know what our book does. Our book might do something similar. There's some notation to indicate that those are the 4 types, and the first number is the number you start with. Let's go back to Babaloon. Remember, we were permuting this where the types were 2, 2, 1, and 2. We were permuting 7 things, this many types of each. Now, let's say I had 4 boxes here. Box number 1, box 2, box 3, box 4. B1, B2, B3, B4. And I wanted to ask you, how many different ways are there to take these letters and throw them in these boxes where I insist you have to have 2 in this box, and 2 in this box, and 2 in this box, and 1 in this box. It seems at first like that might be a different problem. But that's really the same problem, and I want to convince you of that. So I'll say it again, and I'll show you that these 2 problems are the same. The number of ways to distribute, well, I might not have said what I meant a second ago, so listen now. The number of ways to distribute 7 distinct objects. Do I mean that? No. They're non-distinct objects into distinct boxes. I think this is what I mean. And if this isn't what I mean, then I'm going to have to come back to it later because I'll confuse myself. With 2 in B1, 2 in B2, 1 in B3, 2 in B4. I wonder if I mean this. I mean distinct, huh?
In other words, there's just one way to do it.
Yeah, I agree. I mean distinct. Good. Do I mean distinct boxes or non-distinct boxes?
Well, they have to be distinct boxes. You qualify how many are going to be in B3 separately, right?
Yes, I agree. No, but I can just say 2 in one of them, 2 in another, 2 in a third, and 1 in a fourth, and I don't really care about which.
What's the
distinct object, I mean, are B and B distinct objects or not? Because we only have 4 distinct types.
Let me show you what I really mean. This is the B box, this is the A box, this is the L box, this is the O box. Okay? These numbers, think of them as 1, 2, 3, 4, 5, 6, 7. I'm going to put these numbers 1, 2, 3, 4, 5, 6, 7 in these boxes. I'm going to put 1 and say 4 in this box. I'm going to put, pick anything, 2 and 6. Here I get to only put 1 in. 3, and here I got, what do I got left? 1, 2, 3, 4, 5. 5 and 7. Which one of these permutations does this correspond to? It means B is going to be in positions 1 and 3. A is going to be in positions 2 and 6. L is going to be in position 3. And O is going to be in position 5, 7. I don't care whether the numbers go in the box 5, 7 or 7, 5. It's just a big empty box. I just look inside. They're all messed up in there. So the order inside the box doesn't matter. So I want to take 7 distinct objects, distribute them into 4 distinct boxes, 2 in this, 2 in this, 1 in this, 2 in this. And that's exactly the same as permuting these values 7 different ways, where I don't care about the order of the O's or the order of the A's or the order of the B's. All right, I made this much harder than it needs to be. This is a much more exact one-to-one than it seems, yeah. But I want you to see this example that you can think of a permutation problem as a distribution problem. So it is distinct. I had it right the first time. I just got a little confused. They're labeled, B-A-L-O, distinctly labeled. And you want to represent this particular permutation, the Babalu permutation, as a distribution into these boxes.
Right.
So how do you do it?
You go 1, 3, 2, 4.
1, 3, good. 2, 4, 5, 6, and 7. So if I gave you 7 items, and I said, distribute them, you have to put 2 in the B box, 2 in the A box, 1 in the L box, 2 in the O box. Every time you finish doing it, I could write a distinct permutation of those letters up on top that is a one-to-one correspondence with this. And every one of these permutations has one of these distributions, and every one of these distributions has one of these permutations. You have to keep in mind that the order in the box doesn't matter. Right? Everybody understand that? If it did matter, then this wouldn't be the same anymore. Yeah. Joe?
Do you have to put the limitation on how many objects can go in each box?
Yes. Yeah, because if I let 3 objects go in box B, that corresponds to having 3 B's in my permutation. I only have 2 B's. So box B's got to get exactly 2 of these positions from the 7. I have to be very specific about what goes in these boxes.
The equivalency is saying the number of ways that the Babalu could be arranged is equivalent to the number of ways that you can throw 7 boxes, 7 letters in those 4 boxes, given those.
Given these constraints, the number of ways to throw 7 different objects into these 4 boxes, given these constraints, where the boxes are labeled, B-A-L-O, is exactly the same number of ways as you can rearrange these letters into distinct configurations. Again, to start off, I want to do an example. And the example here is going to be just like the regular combinations that we've done before, but now I'm allowed to repeat. So here's what it looks like. Combinations with repetition. Is that how you spell repetition? From 3 distinct types. Let's talk about combinations with repetition from 3 distinct types. And as a particular example, let's say I want to take 8 of these. So combinations, say, of length 8. Length 8. Put it here. Combinations of length 8 with repetition from 3 distinct types. If I ask you how many combinations are there of 3 distinct types where you can't repeat, and I want to take 2 of them, it would be 3 choose 2. Right? But now I'm taking 8 of them, so I'm going to have to be able to repeat. But I don't care about the order this time. This is equivalent to the following problem. You go into a bakery. You want to buy 8 things. You want to buy 8 things to eat at a bakery. We'll make it practical. You want to buy 8 things to eat at a bakery. They sell cookies, brownies, muffins, donuts. They only sell one kind of cookie, one kind of brownie, one kind of muffin. So they got 3 big barrels. That's this bakery. One big guy stands behind the 3 barrels and says, muffin, cookie, or brownie. You say which one you want. He gives it to you, charges you some money. But you want to buy 8 of these things. If you buy 3 brownies, 3 muffins, and 2 cookies, that's one way to get your 8. It doesn't matter whether you buy 3 muffins from the top of the muffin barrel or 3 muffins from the bottom of the muffin barrel. It just counts as 3 muffins. It just matters how many muffins you buy, how many brownies you buy, how many cookies you buy. Okay, everybody get the problem? So how many ways are there to go ahead and get your 8 items taken from the bakery if you can only take from these 3 barrels? This problem, I think, is the coolest kind of problem because it is not obvious when you first think about it, and when you finally see how to do it, it becomes easy. A lot of problems are like that, but this one really connects back to regular old combinations without repetition. And the connection is one of the most powerful tools you have in your bag of tricks. So not only can permutations turn into combinations, but generalized combinations can turn into simpler combinations. And I want to explain how this works by first doing a couple of examples. So let's call these 3 barrels M, cookies, brownies. Okay? Muffins, cookies, brownies. Let's put a couple of possibilities up. We could have, let's say, 3 muffins, 3 cookies, and 2 brownies. That's one possibility. Where's another one? We could have 8 muffins, no cookies, no brownies. Was that Anthony? Likes muffins? All right, just a couple more. 6 here, 1 here, 1 here. All right, everybody see the different possibilities? So the question is, how many of these are there? If I write it like this, it doesn't give you a clue at all. Or maybe it does, but not to me. So how can we write it to give us more of a clue? Here's a different way to write it.
Write each of the numbers as...
But it seems like you could do it as a string, but the only problem is that the order doesn't matter. So
we could...
First,
You mean we could have like we could have some number of M's followed by some number of C's followed by some number of B's, right? And you just have to have a total of 8 of them. But it doesn't connect to what we did last time, because last time we had to have a certain number of M's, a certain number of C's, and a certain number of B's. Here it's the sum that has to be equal to something. So that connection is there, but not so obvious how to exploit it. Yeah.
I tried it with just, if you had just 2 choices.
To make it easier.
Yeah, and then...
then go from there.
And then you could do recursively up to 3.
That's a great strategy. That's a great strategy. Agreed, right. Once you choose the first 2, then you have to choose that number for the last one. So if we made it just 2 choices, then you really just have 1 choice, and then the last one's determined. Should we do Neil's idea? We'll do real pedagogy today. Instead of me just showing you the answer, we'll discover it together. I think Neil's idea is really good. So let's hold off on this problem, switch over here to the side of the board, and deal with a 2 case. How many different ways are there?
9.
You get to choose 0, 1, 2, 3, 4, 5, 6, or 7, or 8 here. And then this is already determined. So 0, 1, 2, 3, 4, 5, 6, 7, 8, that's 9 possibilities. And that's it. It's just 9. So with 2 items, it just seems like it's this plus 1. All right, well, is it illuminating? A little? Does it generalize? Maybe.
Right, now just take the third one, write those possibilities for the third one down, and then you got plus what's left for the 2.
But if you, so let's say we choose 1 here, right? So here's Neil's idea. Neil's idea is that we'll try 0 through 8 for the first one, and then if it's 0, we've got 8 choices left for the last 2. That we can do with a 2 case. If it's 1, we have 7 choices left for the last 2. Right? And if it's 2, we've got 6 choices left for the last 2. This is a good idea, and you will come up with a formula, but as you can see, as the number of things get bigger, this formula becomes a long recursive formula, and it would really be a good direction to go if I had another hour today to follow it. It would be a nice way to go. But I want to short-circuit it for a second.
9 factorial? Or no, 9, the triangle number, 9.
For the 3 cases, you get the triangle numbers added up. The next cases, they kind of get summed up themselves. Well, I don't want to go down this road, even though it's a good road, just because I don't have enough time to do it. But it is a good road to go down. Yeah, Rob, you had a question?
Well, why does it have to be a recursive equation? Doesn't it just look like it's the number of types times the number of bins minus 1 factorial? From what Neil said?
I don't think so, because each of the choices for the first bin gives you a different problem for the other 2 bins. If you choose 0 here, you have a 2-bin problem with 8. If you choose 1 here, you have a 2-bin problem with 7. And if you choose 2 here, you have a 2-bin problem with 6. So for 3 bins, you get the sum of these 2-bin problems for different numbers. And for 4 bins, it's going to be even a bigger sum of 3-bin problems, which will then be in turn a sum of 2-bin problems. So there's not even multiplication here going on. There's a lot of addition here that's going on. Okay. So Neil's saying here, try 0 for this, then the other 2 boxes have to be filled with 8 things. That's a 2-bin problem with 8. If you choose 1 here, then these 2 boxes have to be filled with 7 things. That's a 2-bin problem with 7. So you have to add all those possibilities together, and you don't get a factorial. Or maybe you had a different idea. Well, let me suggest this way of looking at it, which will take us back to something that will short-circuit this very nice excursion that you thought about. And here's the way I want to look at it. The 8 things I'm just going to represent as x's. 6, 7, 8. They are neither muffins nor brownies nor cookies right now. How do I turn them into muffins, brownies, and cookies? I got to divide them into 3 sections, right? How do I divide them into 3 sections? I'll add in a little squiggly line separating them. How many squiggly lines do I need to put in to divide them into 3 sections? 2 squiggly lines. Okay so far? So let's do 611. 611 will be this. 1, 2, 3, 4, 5, 6. That's 611. Okay? That stands for, going left to right is brownies, cookies, muffins. 6 brownies, 1 cookie, 1 muffin. Let's do the next one. 008. Where do the squiggly lines go then? Where are the squiggly lines here? 8. Oh, jeez. Here. 0, 0, 8. 3 sections. This section has nothing, this section has nothing, this section has 8. How do you represent this one? 2, 3, 3. 2, 3, 3. Everybody see what I'm writing down? I'm just writing it down with pictures. I'm taking every one of these ways of distributing the objects and making into this picture. And now I'm going to ask you a different question. How many of these pictures are there? Because if we can count this number of pictures, we can count these things. Doug yelled out 9, choose 2. Does that make sense? 1, 2, 3, 4, 5, 6, 7, 8, 9. We got 10 different places, and the squiggles can go. Can they go anywhere in those Where can they go?
Wait, 10 places? There are 9 places, aren't there? If they're in the same place, if they're
Harumph. Who knows? Let me remind you where we're up to. You can talk amongst yourselves, but here's where we're up to. We're trying to count how many pictures these are, where I have 8 X's and 2 squiggle lines, okay? And they can be presented in any order you want, but I've got 8 X's and 2 squiggle lines. Yeah, Jeff.
If you take the X's and turn them into zeros and the squiggles and put them into ones, then you just have a binary problem.
Okay.
Or if you just, where there's not a squiggle, make it a 0.
Yeah, right, where
Where
there's-
there's a squiggle, make it a 1.
Okay. So I agree. I can turn these into binary numbers, but there's something very specific about these binary numbers, right? I only have 8 of zeros and 2 ones. So did we ever do a problem where we had 2 different types of things, where we had to use exactly a certain number of each type and figure out the different permutations of those types? Yeah, Rob.
Why do there have to be 2 1s instead of
There have to be 2 of these things.
Are we just going to add a special case where the squiggles are on top of each other? Because there's no brownies, say?
They're next to each other. If there's no brownies, say there's, let's do it. Say there's,
I think we're split in half, right?
let's say there's no brownies and there are 6 cookies and 2 muffins. So 6 cookies, squiggle, squiggle, 2 muffins. No brownies in between. You're choosing M things from N. You have N different types. This is going to be the same as M plus N minus 1, choose N minus 1. That's what we just did right now. I want to convince you that this is the same as another kind of distribution. The first problem is the same as the distribution of distinct objects into distinct boxes. And here, see if you can figure it out, it's a distribution of, think of the cookie problem. We're taking 3 boxes of cookies that we're going to bring home with us in a little container. A box for muffins, a little box for brownies, a little box for cookies. Okay? We're taking 8 of our choices. Okay? I have $8. So they say everything costs $1. You guys gave me 8 single dollar bills. I'm bringing them home. What I'm going to do, in order to decide exactly how many cookies, muffins, and brownies I'm going to bring home, is on my way to the store, I take all your 8 single dollar bills and I drop them into one of these boxes. If I drop 3 in the brownie box, it means I'm going to get 3 brownies. If I drop 4 in the cookie box, it means I'm getting 4 cookies, and then I have to drop 1 in the muffin box. So that's this combinations with repetitions of N types, where we're taking M of them, M are the dollars, N are the 3 boxes, is the same as distributing M things into N different boxes. Distribution of M. Are the M objects distinct or non-distinct? They're non-distinct. They're all single dollar bills. It's like those X's. M non-distinct objects. That's distinct from the last example when they were distinct. Distribution of M non-distinct objects into N distinct boxes. This distribution problem is equivalent to this problem. My point of showing you the equivalence of distributions in both these cases is that when you get a distribution problem, you should always be able to convert it to a combination or a permutation. They are really just applications of combinations and permutations. They are not one more thing to memorize. They are just a logical continuation of what you've done. If you want to start memorizing things, you are going to kill yourself in this topic. Here's the things you can memorize if you want to. The formula for regular permutations. The formula for permutations N choose K. The formula for combinations N choose K. The generalized formula for permutations where you have a certain number of each type. The generalized formula for combinations when you're allowed to do repeat. The general formula for permutations when you're allowed to repeat. Distributions of non-distinct into distinct. Distributions of distinct into distinct. distributions of non-distinct into non-distinct. You can memorize a formula for every single one of these. Every single one is a different formula. You can memorize them, and then when you get a problem, you're going to have to, number one, instead of thinking about it from a fresh perspective, all you're going to be doing is saying, which one of these 9 categories does my problem fit in? And you won't have had enough personal experience pulling a problem apart to have any good skill at doing that. So you're likely to end up throwing the problem in the wrong category. Then you're likely to mismemorize the formula. So if you're really lucky, you throw it in the wrong category, mismemorize the formula, use the right formula on it, and get it right. This is the worst way to do this type of stuff. It's a good way if you're desperate. It's a good way if all you really want to care about is I got to get through the next day and I just want to get this problem right. But if you really want to develop these skills, then the way to do it is to concentrate on those 5 principles. To look at these examples as basic examples that come up a lot. And every time you get a new problem, to work on it from scratch until you are reminded of something you've done before. If you're not reminded, then go back and review it. But when you start to get reminded, then go back, then make the connection, and then these things will be inside you. One more word of this proselytizing before I let you go today. I do not remember these formulas. I cannot remember if you gave me a list. Here's all the permutations with repetition, without repetition, distinct objects, non-distinct objects, and you said write down all the formulas. I would get a 40 if you gave me 5 minutes to do that test. I couldn't do it. I would have to think about each one, think about what it means, relate it to the one that I was most familiar with, and then reconstruct the formula as I go. Okay, some things you remember because they come up a lot, but the less you have to remember, the better. You want to just fill your brain with as few principles as possible and just let the neurons do their job. Don't clog it up. All right. Questions about this stuff? Here's where we're up to. We've now finished with what I think are the basic combinatorial principles and the basic combinatorial ABCs. There's a lot there. It takes a lot to digest this stuff. What we're still going to do is using the inclusion-exclusion theorem as a way of milking these principles one step further and doing problems that otherwise would be very hard. And the inclusion-exclusion theorem is really just kind of a generalized complement idea. Then we'll talk about the pigeonhole principle, discrete probability. We've got about 2 to 3 lectures left on this material, and then we're going to move on to number theory in the last unit for this course.